Deep beneath the picturesque landscape of Geneva, Switzerland, lies one of the most ambitious scientific projects mankind has ever undertaken, the Large Hadron Collider, or LHC. This immense machine, buried 574 feet underground, is not only an engineering marvel, but also a key to unlocking the fundamental mysteries of our universe. More than just a particle accelerator, the LHC symbolizes humanity's relentless quest for knowledge and our desire to push the known limits of science. Through this relentless pursuit, we hope to unravel the mysteries of existence, from the origins of matter to the forces that govern reality itself. At over 17 miles in circumference, the LHC is the largest and most powerful particle accelerator ever built. It consists of an underground ring of superconducting magnets designed to accelerate protons to speeds approaching the speed of light. When these protons collide at certain points, they recreate the extreme conditions that existed just moments after the Big Bang. These high-energy collisions allow scientists to peer into the fundamental structure of matter, searching for answers to questions that have puzzled mankind for centuries. By smashing particles together, the LHC provides insights into the building blocks of the universe, particles so small that they cannot be observed by any other means. The LHC is not only a tool for understanding the physical cosmos, it also reflects the delicate balance between human curiosity and the potential dangers that come with scientific exploration. The experiments conducted at CERN, where the LHC is housed, have opened doors to new realms of knowledge, but they also raise profound questions about the risks involved in pushing the boundaries of science. As we venture into the unknown, we must grapple with the ethical and existential challenges that come with such powerful experiments. Recently, physicist Brian Cox, a prominent figure in particle physics, made a statement that caught the attention of the scientific community. He hinted at a mysterious discovery at CERN, although details remain scarce. Could this discovery challenge our current understanding of the universe? Or will it raise more questions than it answers? The LHC is not just a machine. It represents the cutting edge of human knowledge and our attempt to understand the unknown forces that shape our reality. The LHC operates with an almost unimaginable level of precision. Inside the accelerator ring, protons are guided by superconducting magnets cooled to just 1.9 degrees above absolute zero, colder than space itself. This extreme cold is essential for the magnets to operate with the precision required to accelerate the protons to nearly the speed of light. As the protons race around the ring, they travel more than 11,000 times per second. And when they collide, the resulting energies are millions of times hotter than the center of the sun. These collisions create new particles, which are then captured and analyzed by massive detectors placed at key points around the LHC. Among the most famous discoveries made at the LHC is the Higgs boson, often referred to as the God particle. Its discovery in 2012 was a monumental moment in the field of physics, confirming a theory that had been proposed nearly 5 decades earlier. The Higgs boson is crucial to the standard model of particle physics, which describes how the fundamental particles of the universe interact. This particle is responsible for giving mass to other particles, and its discovery provided a significant leap forward in our understanding of the universe. But the LHC's mission doesn't end with the Higgs boson. The accelerator continues to probe deeper, seeking answers to even more elusive questions. One of the biggest mysteries the LHC hopes to solve is the nature of dark matter. Dark matter is an invisible substance that doesn't emit, absorb, or reflect light, making it impossible to detect by conventional means. Despite its invisibility, dark matter is thought to make up about 27% of the universe, far more than the ordinary matter that forms stars, planets, and everything we can see. Scientists hope that the LHC experiments will allow them to create dark matter particles in the laboratory, providing clues that could revolutionize our understanding of the cosmos. Another tantalizing frontier the LHC will explore is the possibility of extra dimensions. According to some theoretical models, our universe may consist of more than the 4 dimensions we're familiar with, 3 dimensions of space and 1 of time. These extra dimensions could help explain several mysteries of physics, including why gravity is so much weaker than the other fundamental forces. If extra dimensions exist, the LHC may be able to detect them by observing how particles behave at incredibly high energies. Proof of extra dimensions would fundamentally change our understanding of reality and open up new areas of scientific exploration. With such groundbreaking experiments come significant risks and ethical concerns. One of the most controversial possibilities involves the creation of microscopic black holes. Black holes are regions of space where gravity is so strong that not even light can escape. And the idea that the LHC could create such entities, even on a tiny scale, has sparked both excitement and concern. Scientists at CERN have assured the public that if any black holes are created, they will be unstable and disappear almost instantly. Extensive safety checks have been conducted to ensure that these experiments pose no threat to our planet or the universe. However, the very idea of creating a black hole, no matter how small, has led to heated debates and raised fears about the potential consequences. To understand why the LHC could create a black hole, we need to understand the mechanics of particle accelerators. When protons are accelerated to near light speed, their energy becomes so immense that it can warp the very fabric of space-time. Imagine a trampoline with a heavy object placed on it. The fabric stretches under the weight, creating a dip. If the object is heavy enough, it can create a well that pulls in everything nearby. This is a simplified analogy of what could happen in the LHC, where the energy of the protons could theoretically create a tiny black hole. Even renowned scientists have expressed concern about the potential risks of the LHC. The late Stephen Hawking warned of a scenario in which the Higgs boson could become unstable at extremely high energy levels, leading to a catastrophic event known as vacuum decay. This hypothetical event could trigger a sudden and inexorable change in the nature of the universe, annihilating everything in its path. Although the probability of such an event is considered extremely low, the mere possibility has led to serious ethical discussions within the scientific community. Another prominent voice in the field of cosmology, Sir Martin Rees, has also expressed concerns about the potential risks associated with particle accelerators. In his book On the Future, Rees addresses the potential risks associated with experiments that challenge the boundaries of physics. He investigates the potential for a destructive phenomenon known as vacuum instability to result in a catastrophic phase transition within the universe. Notwithstanding these concerns, the scientists at CERN maintain that the probability of such an occurrence is exceedingly low and that the potential benefits of the research outweigh the risks. As we stand on the precipice of new discoveries, it is evident that the Large Hadron Collider will continue to play a pivotal role in expanding our understanding of the universe. However, as we venture into uncharted territory, it is imperative that we remain mindful of the responsibilities that accompany such knowledge. The LHC's power enables us to probe the depths of reality in ways that were previously deemed impossible. Nevertheless, with this power comes an obligation to consider the potential consequences. One of the most perplexing questions that the LHC is designed to answer is that of the matter-antimatter asymmetry of the universe. In accordance with the fundamental principles of physics, the Big Bang Theory predicts the creation of equal amounts of matter and antimatter. However, the subsequent annihilation of these two forms of matter would have resulted in the absence of any remaining cosmic matter. Nevertheless, our universe is predominantly constituted by matter, with no discernible presence of antimatter. The experiments conducted at the LHC, particularly those with the LHCb detector, are designed to investigate this imbalance and provide insight into one of the most profound mysteries of cosmology. Additionally, the LHC is contributing to our understanding of cosmic rays, which are high-energy particles that constantly bombard the Earth from outer space. These particles, which include protons, electrons, and atomic nuclei, travel through space at nearly the speed of light, yet their origins remain shrouded in mystery. By studying high-energy collisions in the LHC, scientists aim to simulate the conditions that produce cosmic rays, thereby elucidating one of the most enigmatic phenomena in astrophysics. The potential for discovery at the LHC remains vast, offering promising avenues for further investigation and understanding. Upgrades to the collider are already being considered, with the High Luminosity LHC (HL-LHC) planned to increase the number of collisions, thereby facilitating the collection of even more data. This forthcoming phase of the LHC's operation may reveal hitherto undiscovered particles and phenomena. However, the LHC represents merely one step in the broader journey of scientific exploration. Plans are already underway for even more ambitious projects, such as the proposed Future Circular Collider, FCC, which would be larger and more powerful than the LHC. The Large Hadron Collider, LHC, is a testament to international collaboration, representing the work of thousands of scientists, engineers, and researchers from around the globe. CERN, established in 1954, has evolved into one of the most esteemed research institutions globally, comprising 23 member states and numerous scientists engaged in investigating the fundamental forces that shape our universe. The LHC represents the pinnacle of CERN's endeavors, yet it constitutes merely one component of a comprehensive network of particle accelerators dedicated to the objective of propelling subatomic particles to unprecedented velocities. The Large Hadron Collider is more than a machine. It is a symbol of humanity's insatiable curiosity, our determination to understand the universe, and our willingness to push the boundaries of what is possible. It allows us to ask questions about the nature of existence that would have been unimaginable only a few decades ago. However, as we continue to push the limits of scientific exploration, we must do so with caution.